this lesson, we are going to discuss torque. What is torque and how do we find it? But first, let's consider the types of motion we've discussed in this class so far. And up to this point, we've only been talking about movement that we would categorize as translational motion, meaning that the center of mass of an object is moving through space. So examples of this type of motion would be something like a rocket launching through the sky, right? So a rocket, as it launches through the sky, all points of the rocket, including its center of mass, are moving upward, and it is moving upward relation to all of the objects in its surrounding. Some other examples would be a bullet flying through the air, a sprinter running across the track, and the moon orbiting the Earth. All of these examples have the whole object moving through space relative to the objects around them. However, another type of motion would be rotational motion, and this is movement of an object around an axis of rotation, which does not necessarily involve the object moving through space relative to other objects around them. So for example, if we had a Ferris wheel going around, a Ferris wheel will rotate around its central axle, around its central point, but if we think about it being next to the roller coaster in the amusement park, as the Ferris wheel rotates, it is not changing its position relative to the roller coaster. It's not getting closer or further from the roller coaster as the Ferris wheel rotates. Same thing with an ice skater spinning. An ice skater can spin in one spot. They will spin around a central axis, and their arms and legs and everything will spin around that axis, but they won't change the location as they go. And finally, the rotation of a car tire. A car tire can rotate without it moving, though often as a car moves forward, the tire is rotating around its central point and the whole car, including the tire, are moving forward in space. So that would be an example of a combination of rotational and translational motion. And because we've only discussed translational or linear motion so far, that means that when we've been thinking about objects, we've been able to reduce their three-dimensional shape down to just a single point in space, like we've done in our free body diagrams. And in doing so, we've limited our exploration to linear or translational motion and the linear or translational acceleration, and haven't worried about the rotational motion of the objects themselves. So we have simplified our concept of equilibrium, which, just to review, we can have a static equilibrium where an object is at rest and all the forces acting on it are balanced, or there's zero net force, and so it will not begin moving. Or we can have instances of dynamic equilibrium where an object is already in motion, already has a velocity, but again, because all the forces acting on it are balanced, or it has no net force, because of that, it will not change its state of motion, so it will continue to move at the same speed and direction, in the same direction, or travel the same velocity. And so far, we have oversimplified our conception of equilibrium because we have treated so far the absence of a net force or having zero net force acting on an object as the only condition for equilibrium. But zero net force simply means it will have zero linear or translational acceleration. Let's take a look at an example where we have zero net force, but we may end up seeing some type of acceleration occur. So if we take a look at this hockey stick, if this hockey stick is on ice and we apply some force to it, then it will accelerate. And in this example, we have two forces, one coming from the right, one coming from the left. And they both are the same magnitude because there's the same size arrow, but they're going in opposite directions. So there's zero net force on this hockey stick. And since there's zero net force, then obviously we would have zero acceleration, right? Acceleration equals zero. However, let's shift these arrows, these forces, so that now one of them is applied higher up on the hockey stick and one of them is applied lower. We intuitively know that even though we still have zero net force, we're actually going to see a change in the state of motion of this hockey stick, right? It's going to begin rotating, in this case, in a clockwise manner. And so we have no acceleration under one condition where we have no net force, and we have an angular or a rotational acceleration under the second condition, even though in both of them we have a net force of zero. And torque is what we call when a force applied to an object causes that object to rotate around or about an axis. Torque which we symbolically represent with the Greek letter tau, is the measure of the effectiveness of a force in changing or accelerating the rotation of an object. And it's the rotational equivalent of force. So, where force will cause an acceleration, a linear acceleration of an object, torque will cause a rotational acceleration of that object. And we can give a mathematical model for torque, which is as follows: that torque, or again, that Greek letter tau, equals R, which is the distance from the pivot point to where the force is applied. I'll show you what that means in 1 second, times the force applied to the object, times the sine of the angle between the force and the vector R. So, and ultimately, torque will be measured in Newton meters because we're taking radius, which is measured in in meters, times force, which is measured in newtons, and then the sine of an angle will be without units. So, torque is in newtons times meters, or meters times newtons, but we generally express this in newtons times meters. So if we take a look at an example here, we've got, again, our hockey stick, and now we've stuck a nail into the hockey stick. So this is the axis of rotation. So as the hockey stick rotates, it's going to rotate around this central point, right? And so if we apply a force here, that force is going to have some magnitude, and that will be our force. And then that force is going to be applied to some distance away from that pivot point, away from that axis of rotation, and that is our distance, or our distance vector, or R. And then finally, those two, the force and the radius, are going to have some angle between them, and that angle is what will go into that sine function. So to find the torque that will cause this rotation, this counterclockwise rotation that this hockey stick will experience, we would take the radius times the force times sine of that angle between them. And our torque is going to depend on where the pivot point is located. So in scenario B, if we take and we put a new nail into the hockey stick and we place it higher on the hockey stick instead of lower, then if we apply that same force, we'll end up with a different R, a different distance from our pivot point to our force, and we'll end up with a different rotation. We'll end up with a clockwise rotation this time. So a question for you is, what angle between the force and the radius will maximize the amount of torque for a given force and distance? And the answer there is, unsurprisingly, 90 degrees. So 90 degrees, sine of 90 would give us 1. Anything other than 90 degrees would give us less than 1, right? So up here over in example B, we have a 90-degree angle between the force and the radius there. And so that means that we'll have the most amount of torque we can get from this particular force. Whereas over here, in example A, we will have some angle between a force and a radius. So this would be less than the maximum amount of force or torque that we can exert from that force. And torque is the cross product of the distance vector r and the force vector F. And a cross product in vector calculus multiplies two vectors with the sign of the angle between them, and they result in a new vector. So torque is a vector, and you can express it as a cross product like this, though you don't have to worry about that. This is the equation that we'll be using. And importantly, since torque has a direction, we will, for now, be using our direction as either clockwise or counterclockwise, are the directions we will use for torque, though eventually we'll kind of develop this understanding of direction for torque. So then you can think about where a doorknob is placed at a door and why it's at the end of a door, furthest away from the hinge rather than in the middle or towards the hinge. And you can think about these different diagrams of torques being applied to a door, and you can consider and rank which one is highest and which one is not. And if you're interested in the answers there, you can head on over to OpenStax, the AP Physics book that we use for this course. Another way to describe the components of torque is with lever arm, or otherwise known as moment arm. And this is the shortest distance from the pivot point to the line along which the force is acting. So if we think about this force F acting again on our hockey stick that is going to rotate around our pivot point created by that nail, then that force has a line that's extending out from it. And at some point along that force, there's going to be a perpendicular distance between the line of that force and the pivot point. And that perpendicular distance is what we would call our lever arm or our moment arm. So it's the shortest distance between that line of force and the pivot point. And If we calculated this, we could find that distance by taking r, our radius, right, and multiplying it times sine of that theta, since it's just a triangle, and r is our hypotenuse, and then this is our side that's opposite to the theta, the angle that we have, right? And if we go and we plug this into our torque equation up here, then we know that r times sine theta is that perpendicular R or lever arm. So we can make that into, we can condense this equation to say that our lever arm or R perpendicular times theta is the same thing as torque. So let's do an example problem here. Let's say that your brother left the front door open at a 25-degree angle. So I'm going to say that theta equals 25 degrees, this angle between force and radius. You want to open it further, but you press parallel to the wall for some reason. So rather than pressing into the door at a 90-degree angle, you press parallel to this wall. And you press on it with a force of 25.0 newtons at a point that is a radius r of 46.0 centimeters away. And 46.0 centimeters is the same as 0.460 meters, right? So our first question is, what is the perpendicular lever arm length of the applied force? And we know that our r perpendicular, or perpendicular lever arm, equals our radius times sine of theta, right? So if we take our radius is 0.460 centimeter, 0.460 meters, and multiply that times a sine of 25 degrees. And we plug that into the calculator, we get something about 0.194 meters, which is what we expected to get. And then we also can find the torque that we apply to the door. We can start with just our radius, or now that we have our perpendicular lever arm length, we can use this equation right here, which says that our torque equals our perpendicular lever arm length times force. And we already found our perpendicular lever arm length is 0.194 meters. And obviously that's going to be closer than our original 46 meters, right? Because look, since we're going parallel to the door, this side is going to be so much closer than our hypotenuse over here. And we'll multiply that perpendicular lever arm times the force, which is 25.0 newtons, and we should end up with a torque of about 4.86, and this is newtons times meters, and that gives us Newton meters. All right, and now that we have discussed torque, we can have a complete picture of equilibrium, because for true equilibrium with regards to both linear or translational acceleration and with regards to angular/rotational acceleration, we actually need two conditions met. The first of which is what we've always known, that net force needs to equal zero, right? So all forces acting on an object need to be balanced in all directions so that the center of mass of that object is not going to be accelerated in a linear or translational sense. But secondly, to prevent any rotational motion, we also need the net torque on an object to be zero. So all the torques have to be balanced in all directions. And this means that in a simple one-dimensional rotation problem, we can break this down to clockwise and counterclockwise torques around a single pivot point. So if we think about, again, maybe our hockey stick on a pivot point like a nail, then if we apply a force in this direction, that's going to give us, this force one, it gives us a torque in the counterclockwise direction, right? So if that's our only force, we're going to start rotating in that counterclockwise direction. However, if we take and we have two forces, a second one going in the opposite direction that's equal and opposite to that one, so a negative F1, that's going to give us a torque in the clockwise direction. And if those two things are equal, then we have a net torque of zero, and that means that our object will not experience any angular or rotational acceleration, in addition to no linear or translational acceleration, so long as net forces are zero. So if our net force is zero and our net torque is zero, then we'll have our object will truly be at equilibrium. All right, let's put this into practice with one more Practice problem. So we've got two children balancing on a seesaw, and the seesaw is of negligible mass. So we're not going to take into account the mass or the weight of the seesaw in this problem. The first child has a mass of 26.0 kilograms, and he sits at a radius of 1.60 meters away from that pivot point on the seesaw. So if our child has a mass of 32.0 kilograms, then we want to figure out what that radius of the second child is away from that pivot point. How many meters is she away from that pivot point? So we can take, and knowing what we know that if everything's going to be balanced, then our net torque has to equal 0, right? Which means that whatever torques we have in, which means that since our net torque is whatever torque we have in the clockwise direction minus whatever torque we have in the counterclockwise direction, that those two have to be equal, right? Our clockwise torque has to equal our counterclockwise torque. So let's think about which one of these children will be providing the clockwise, which one will be providing the counterclockwise. And if we look at child 2 over here, if we were allow her weight to rotate our seesaw, it would rotate like this, right? Or in a clockwise direction. So that means that her force of gravity, or m2 times g, is going to be the thing that's providing that that clockwise torque, right? And then on the other side, our child 1 would be rotating the seesaw in a counterclockwise direction. So that means that his force of gravity, or m1 times g, will be providing the torque that is counterclockwise, right? So if we rewrite this as our torque in the clockwise direction equals our torque in the counterclockwise direction, and we rewrite everything using our equation for torque, we got our clockwise torque is going to be our student 1, right? And that force of gravity on child 1 is his mass times g, and then his radius is radius 1, and then obviously his angle between his weight and the radius is going to be that sine of theta 1. However, that angle is 90 degrees, right? So he's at a 90-degree angle between the length of the bench and his force. There's a 90-degree angle there. So that's going to end up just being 1. And that will equal the force of child 2, since she's providing the clockwise torque. So that means we'll take whatever force is providing the clockwise torque times the radius of the clockwise torque. No. So that means that for the clockwise torque, we will take the force that child 2 is exerting, right, which is her force of gravity, which is her mass, m2g, times her radius, which is r2, right, times the sine of the angle between her and her force and the radius. But if we look at her force and the radius, there's a 90-degree angle there. So that means this is just going to become 1. Right? And we'll set that equal to the counterclockwise torque, which again is coming from our child 1 over here, which is his force of gravity, or m1 times g, times his radius, which is r1, and then the angle between him, his force, and his radius, right? Which again, his radius is is horizontal, and his force is applied exactly vertical. So there's a 90-degree angle there. So we are going to, so that will also become 1, right? And so that means that we end up with an equation that looks like this: m2g times r2, which is our unknown, right, equals m1 times g times r1. And our g's cancel out, and if we get rid of m2 over on the left, then we end up solving for what we want to solve for, which is r2, and that'll equal m1 over m2 times r1. And we get a nice ratio there of our masses. So our child 1's mass divided by child 2's mass, and then times the radius of child 1.60 meters. And from that, we can get an answer of about 1.30 meters if we plug that into our calculator. So then a second to build on top of this, we can take a look at a second part of this problem, which is what is the force of the pivot by the seesaw? It's provided by the seesaw's pivot. What is the support force exerted by this force exerted by the force of the pivot, right? So then to explore a little bit further, we can think about, well, there also has to be a force here exerted by the pivot that's pushing back up against the weights of our two children, right? And against the weight of the seesaw itself, though in this case, remember we said our seesaw's mass is negligible, so it will have no weight. And so our second condition for equilibrium was met by having a net torque of 0. But in this case, for the seesaw not to be accelerating down or upward, then we need our first condition of equilibrium, which is that our net force equals 0, right? Which means that any upward forces have to equal the combined forces going downward. In this case, that means that our upward forces, we can think about F up minus F down. In this case, our one upward force is that force of the pivot, so that's FP, minus the two forces going downward, right? The weight of child 2, or M2G, and also going downward, so also subtracted from that force of the pivot, is the weight of our first child, M1 times G, right? So if all that equals 0, then that means we can set our forces of pivot equal to M1G plus M2G, or 26 kilograms times G plus 32 kilograms times G. And we would get in the end that those two forces of gravity of the two children combined would give us around 568 newtons, is what that seesaw's pivot needs to be pushing back up to maintain the state of equilibrium for the seesaw itself. All right, and then lastly, to practice this further, we have a problem set attached here that you can take a look at, and there are videos associated with those problems as well. Thank you for paying attention for this lesson.